Hi there, hope you're doing fantastic. And this is the second lecture for conservation of momentum under mechanics. And we'll see some more concepts that we have not seen in the first lecture. So here are the topics that we are yet to see. So in the first lecture, we have seen about center of mass, position of center of mass, motion of the center of mass, law of conservation of linear momentum. And in this lecture, we'll be seeing about variable mass, impulse, and collision in detail. So let's get going. Variable mass. In our discussion of the conservation of linear momentum, we have so far dealt with the system where the mass remains constant. We now consider those systems where mass is variable, that is, those in which the mass enters or leaves the system. A typical case is that of the rocket, from which hot gases keep on escaping, thereby continuously decreasing its mass. In such problems, you have nothing to do but apply a thrust force to the main mass in addition to all other forces acting on it. This thrust force is given by this formula. Ft, which is the thrust force, equals V relative into dm by dt. Here, V relative is the velocity of the mass gained or mass ejected relative to the main mass. In case of rocket, this is sometimes called the exhaust velocity of the gases. dm by dt is the rate at which mass is increasing or decreasing. The expression for thrust force can be derived from the conservation of linear momentum in the absence of any external forces on a system as follows. Suppose at some moment t equals t, mass of a body is m. So here's the picture. This is some body, a random body with mass m. So at some moment t, mass of this body is m and its velocity is v. After some time, that is t equals t plus dt, we have its mass becoming m minus dm and velocity becomes v plus dv. The mass dm is ejected with relative velocity vr. Absolute velocity of the mass dm is therefore vr plus v plus dv. If no external forces are acting on this system, then the linear momentum of the system will remain conserved, or we can write it as pi equals pf, that is, the initial linear momentum equals the final linear momentum. So this can be written as m into v equals m minus dm, that is the mass of this body after losing some mass, into v plus dv plus dm into vr plus v plus dv. Upon distributing each term, we get this expression, and finally we get mdv equals minus vr dm. Dividing both the sides by dt, we get mdv by dt equals vr into minus dm by dt. So this term to the left is called thrust force. And this term, that is minus dm by dt, is nothing but the rate at which the mass is being ejected. So now you take up an exercise of finding the the exhaust velocity of gases in a rocket propulsion. Proceed in the same manner and you'll be getting the answer. Yes? Now we'll move on to the next topic, impulse. Consider a constant force F, which acts for a time t on a body of mass m, thus changing its velocity from u to v. Because the force is constant, the body will travel with constant acceleration a, where F equals ma from Newton's second law. And we all know that at equals v minus u. So from these two equations we get F by m into t equals v minus u. And finally we get, that is, by taking m to the RHS, we get Ft equals mv minus mu. The product of the constant force F and the time t for which it acts is called the impulse J of the force, and this is equal to the change in linear momentum which produces it produces. So we can write this as impulse vector J equals the force, that is the constant force, into time, which is equal to the change in linear momentum, which can be written as the final momentum minus the initial momentum. Now moving on to instantaneous impulse, there are many occasions when a force acts for such a short time that the effect is instantaneous. Example, a bat striking a ball. In such cases, although the magnitude of the force and the time for which it acts may each be unknown, but the value of their product, that is impulse, can be known by measuring the initial and final momenta. Thus we can write vector J equals integral f dt, which is nothing but the change in linear momentum again. So we have Pf minus Pi. Regarding the impulse, it is important to note that the impulse applied to an object in a given time interval can also be calculated from the area under the force time, that is the Ft graph, in the same time interval. Yes? So now we'll move on to the next topic, which is collision. So this is a very important topic. You'll be getting more sums to solve in collision in your JEE mains. So contrary to the meaning of the term collision in our everyday life, in physics it does not necessarily mean one particle striking against the other. Indeed, two particles may not even touch each other and may still be said to collide. All that is implied is that as the particles approach each other, first, an impulse, that is a large force for a relatively short time, acts on each colliding particles. The total momentum of the particles remain conserved. The collision is in fact a redistribution of total momentum of the particles. Thus, law of conservation of linear momentum is indispensable in dealing with the phenomenon of collision between particles. Now consider a situation as shown in this figure. The two blocks of mass m1 and m2 are moving with velocities v1 and v2 initially. Here v2 is less than v1, and they are moving along the same straight line in a smooth horizontal surface. A spring is attached to the block of mass m2. Now let us see what happens during the collision between these two particles. In the first image, you can see that the block of mass m1 is behind m2. Since v1 is greater than v2, the block will collide after some time. Later, the spring is compressed, as in this diagram. The spring is compressed. The spring force F equals kx acts on the two blocks in the directions, that is in the opposite directions. So for this block, the force is towards left, and for this block, the force F equals kx is towards right. This force decreases the velocity of mass m1 and increases the velocity of mass m2. Then the spring will compress till velocity of both the blocks become equal. So that is what is depicted in the second image. So at maximum compression, say xm, velocities of both the blocks are equal, that is v. The spring force is still in the directions as shown, as I explained earlier. That is, the velocity of block m1 is further decreased and that of mass m2 is increased. The spring now starts relaxing. And now we will come to the third image. The two blocks are separated from one another. Velocity of block m2 becomes more than the velocity of block m1. That is, now v2 dash, or here as depicted is v2f, becomes greater than v1f. Now the equations which can be used in this situation are as follows. Assuming the spring to be perfectly elastic, following two equations can be applied in the above situation. In the absence of any external force on the system, the linear momentum of the system must remain conserved before, during and after collision. So therefore we have this first equation, m1 v1 plus m2 v2 equals m1 plus m2 into v equals m1 v1 dash plus m2 v2 dash. Secondly, in the absence of any dissipative forces, the mechanical energy of the system will also remain conserved. So therefore, we have the second expression, that is, the sum of the kinetic energy of the two blocks initially must equal the sum of the kinetic energy of the two blocks finally. Therefore, we have half m1 v1 square plus half m2 v2 square equals half m1 plus m2 the whole into v square plus half kxm square. So this is during collision. That's why we have the energy stored in the spring as well. And then we have half m1 v1 dash square plus half m2 v2 dash square. Yes. So in the above situation, we have assumed spring to be perfectly elastic. That is, it regains its original shape and size after the two blocks are separated. In actual practice, there is no such spring between the two blocks. During collision, both the blocks or bodies are a little bit deformed. This situation is similar to the compression of the spring. Due to deformation, two equal and opposite forces act on both the blocks. These two forces redistribute their linear momentum in such a manner that both the blocks are separated from one another. This collision is said to be elastic if both the blocks regain their original shape and size completely after they are separated. On the other hand, if the blocks do not return back to their original form, the collision is said to be inelastic. If the deformation is permanent and the blocks move together with the same velocity after the collision is said to be perfectly inelastic. Now we'll move on to the types of collision. Collision between two bodies may be classified in two ways. The first classification is elastic collision and inelastic collision, and the second classification is head-on collision and or oblique collision. As discussed earlier, also, collision between two bodies is said to be elastic if both the bodies come to their original shape and size after collision. That is, no fraction of mechanical energy remains stored as deformation potential energy in the bodies. Thus, in addition to the linear momentum, kinetic energy also remains conserved before and after collision. On the other hand, in an inelastic collision, the colliding bodies do not return to their original shape and size completely after collision, and some part of the mechanical energy of the system goes to the deformation potential energy. Thus, only linear momentum remains conserved in case of an inelastic collision. Further, a collision is said to be head-on or direct if the directions of the velocity of colliding objects are along the line of action of the impulses acting at the instant of collision. If just before collision at least one of the colliding objects was moving in a direction different from the line of action of the impulses, the collision is called oblique or indirect. So problems related to oblique collisions are usually not asked in many tests. Still, it's better to know about them. First, we'll see about head-on elastic collision. Let the two balls of masses m1 and m2 collide each other elastically with velocities v1 and v2 in the directions as given here. Their velocities become v1 dash and v2 dash after colliding along the same line. Applying conservation of linear momentum, we get m1 v1 plus m2 v2 equals m1 v1 dash plus m2 v2 dash. In an elastic collision, kinetic energy before and after collision is also conserved. Hence, we have the second expression, that is half m1 v1 square plus half m2 v2 square equals half m1 v1 dash square plus half m2 v2 dash square. So on solving these two equations, we get the final velocity of the two balls. v1 dash will be equal to m1 minus m2 by m1 plus m2 times v1 plus 2m2 by m1 plus m2 times v2. Similarly, v2 dash will be equal to m2 minus m1 by m1 plus m2 times v2 plus 2m1 by m1 plus m2 times v1. Now we'll move on to the next topic, the next type, that is head-on inelastic collision. As we have discussed earlier also, in an inelastic collision, the particles do not regain their shape and size completely after collision. Some fraction of the mechanical energy is retained by the colliding particles in the form of deformation potential energy. Thus, the kinetic energy of the particles no longer remains conserved. However, in the absence of external forces, law of conservation of linear momentum still holds good. Suppose the velocities of two particles of masses m1 and m2 before collision be v1 and v2 in the directions as shown. Let v1 dash and v2 dash be their velocities after collision. So the law of conservation of linear momentum gives m1 v1 plus m2 v2 equals m1 v1 dash plus m2 v2 dash. From this we get the collision is said to be perfectly inelastic if both the particles stick together just like this after collision and move with same velocity v, or say v dash, as shown in this figure. So now we get m1 v1 plus m2 v2 equals m1 plus m2 times v dash. So v dash is the final velocity of both the particles. V dash equals m1 v1 plus m2 v2 by m1 plus m2. Newton's law of restitution. When two objects are in direct, that is head-on impact, the speed with which they separate after impact is usually less than or equal to their speed of approach before impact. Experimental evidence suggests that the ratio of these relative speeds is constant for two given set of objects. This property formulated by Newton is known as the law of restitution and can be written in the form separation speed by the approach speed equals E. The ratio E is called the coefficient of restitution and is constant for two particular objects. In general, E always lies between 0 and 1, that is, E is greater than or equal to 0 and less than or equal to 1. If E is 0 for completely inelastic collision as both the objects stick together. So their separation speed is 0 or E equals 0. E equals 1 for an inelastic collision, as we can show that V1 dash minus V2 dash will be equal to V2 minus V1. That is, separation speed will be equal to approach speed, and therefore we'll have E equals 1. Let us now find the velocities of two particles after collision if they collide directly, and the coefficient of restitution between them is given as E. Now applying the conservation of linear momentum as before in the previous slide, just like this, and also applying the law of restitution, that is, separation speed equals E times the approach speed. By using this expression, we'll finally end up getting V1 dash equals m1 minus E times m2 by m1 plus m2 the whole into V1 plus m2 plus E m2 by m1 plus m2 times V2. Similarly, the final velocity of second particle will be equal to m2 minus E m1 by m1 plus m2 times V2 plus m1 plus E m1 by m1 plus m2 times V1. Now we come to the final topic, that is oblique collision. During collision between two objects, a pair of equal and opposite impulses act at the moment of impact. If just before impact at least one of the objects was moving in a direction different from the line of action of these impulses, the collision is said to be oblique. So in the figure, two balls collide obliquely. During collision, impulses act in the direction as shown, that is, they act along this direction. Yes? Henceforth, we will call this direction as common normal direction and a direction perpendicular to it, that is this direction, as common tangent. Following 4 points are important regarding an oblique collision. A pair of equal and opposite impulses act along common normal. Hence, linear momentum of individual particles do not change along common normal direction. If mass of the colliding particles remain constant during collision, then we can say that linear velocity of the individual particles change during collision in this direction. The second point is, no component of impulse act along common tangent direction. Hence, linear momentum or linear velocity of individual particles, that is, if mass is constant, remain unchanged along this direction. The third point is, net impulse on both the particles is 0 during collision. Hence, Net momentum of both the particles remain conserved before and after collision in any direction. And the fourth point is, definition of coefficient of restitution can be applied along the common normal direction. That is, the relative speed of separation equals E times the relative speed of approach. Here E is the coefficient of restitution between the particles and between the particles. So by this we come to the end of this chapter. Try to solve as many sums as possible, and you can find the content of this lecture in the description. Also find attached the questionnaire for this chapter. Try to solve all the 10 questions without seeing the solution if possible. Thank you.